morning, students. Let's talk about last week. We approved statements about search and learned about a big. We also covered more on a phrase. I'm glad you have finished your mid-semester the test. Thanks you, Dr. Cohen, for this opportunity to address the class. I hail the foundations of where I'll go. God bless the university. God bless America.
Welcome to another class of Foundations of Algorithms. Today's historical figure is Claude Elwood Shannon. He was at MIT writing his master's thesis when he uncovered a mechanism of analyzing circuits not by pictorial representations, but by their analytic algebraic representation, building on George Boulos's formalization of binary algebras. Claude Shannon was also a cryptographer and a noted contemporary of Alan Turing, and was substantially involved in the effort to break the Enigma cipher, the German cipher that we talked about earlier in semester during World War II. Shannon is famous also for the theory of information entropy. Now, this is somewhat distinct from the theory of entropy that you may have learned about in chemistry or physics, although there are links between the two. This became a key factor in the analysis of modern machine learning algorithms, as well as in cryptography. So Claude Shannon here is another one of these important figures that hopefully we'll learn a little more about as some of the material in our course intersects with his work. So now we're going to turn back to Big O proofs, and I know we got a little lost in these last week, but don't worry, we have very steady seas and clear sailing ahead of us. So while we're on the ship of Big O, I should get our oars ready to keep rowing in order so that we can chart our clear waters ahead. And while we're on the topic of nautical metaphors, when we're on a ship, one should be very clear and aware that, oh my God, what is this?
This is a mutiny. I'm taking over for today's lecture, so round of applause for me. Mutiny. Yeah, so what I'm doing today is a friendly mutiny. It's with permission, so it's not really a mutiny. I'm going through some algorithm complexity. I think some of you are well on top of this, while others are not. So I'm hoping to kind of fill in some gaps that you might have. When we're talking about algorithmic efficiency, there are two main things that we look at, and I'm going to focus more on the time efficiency or time complexity. So time complexity is the amount of time taken by an algorithm to run. Are you able to hear me better if I do it this way? I'll do it like this. So amount of time it takes for an algorithm to run as a function of the length of the input to the algorithm, right? And usually for this, we will define some elementary operation, some basic operation that you would repeat over and over again in your algorithm. Just basically the basic part of your algorithm does all of the work. And counting the number of operations here gives you an estimate for how much your algorithm does, like how much time your algorithm spends to run. So as an example, as we covered last week, or Shannon covered last we've got linear search, or really searching an array. We find an element in an array if it exists. So for example, we could find 2. And where is 2? Well, 2 is in the middle of the array. If we're going to do a linear search, we're just going to go through the array one by one. So 9, 6, 5, 3, 2. We found 2, right? Or we could find 13. But 13, I don't know if you can tell, it's not in the array, right? Okay, yeah, so for 13, can't find it in the array. So how long would that take to confirm that we can't find it in the array? Anyone want to try and shout that out? How many elements through the array do we have to go to confirm that 13 is not in the array? Say again. 9, yeah. So how big is the array? 9, right? So what do we think the worst case complexity of a linear search is? Well, for an array of length 9, it is 9. Good. So yeah, we showed finding 2, we just loop through the array like that. And we get 5 comparisons. For 9, we have to finding 9. So the first element in the array, so we get it straight away. So this has time complexity of 1. If we try and find 1, we fail to find it. It takes 9 operations, and we don't find it. So we have 3 things. We have the best case, we have the worst case, and it might be tempting to hope for the best case, but if we're being professionals, we should aim for the worst and plan for the worst. And there's your linear search function, pretty simple function. Hopefully, well, we actually got you to do something similar to this on the mid-semester test with, I believe, question 3. So we're just finding one element here, so we just have a loop that goes through every element. And if we find the target, we return that element, and otherwise we return not found. Great. So what would be the, I'm going to skip that slide for a sec. So when we're talking about runtime time complexity, the running time of the algorithm, we set this to be T of n. So this function T of n represents basically how many operations does, or how long does our algorithm take to run? And this is comprised of the time it takes to execute our basic operation multiplied by the number of those basic operations that we've done. So imagine for here, what would be the basic operation here? There's a few candidates. Does anyone want to have a shout it out? Where on the code is our basic operation? The if line? Where specifically? The return I or the a of I equals target? Yeah, so how many times will this basic operation happen when we execute this function? Is it guaranteed to be the same number of times every time, or does it depend on the input? Yeah, so we showed literally just before, depends on what our array is, right? So we could either have it so that, well, this a of I equals target is going to execute however many times we have to check that the current array element is equal to our target. So in the worst case, this would happen n times. We have to go through the whole array and fail to find the element. Or in the best case, it only happens once. We've found the element immediately. So we say that we were counting the number of operations here, but the actual cost of the operation doesn't really matter. Because I could run this function on my computer, which is pretty fast, or I can run it on a potato and it'll be very slow. And the cost is a variable there, but the actual number of operations is the same. So we're analyzing algorithms. We focus more on the number of operations rather than the cost of the basic operations themselves. So we can make the approximation that the cost of the algorithm, the running time of the algorithm is equal to the cost, the number of operations that we're executing. So since computers have different speeds, the rate of the growth is the most important. So what we're interested in is analyzing how this function grows when n is large. And this is where we can have a look at a specific example. So let's say we have the running time of some algorithm, some function is 12 times n squared plus 2000 log n plus 900 n, right? And we're going to have a look and see which part of this function is growing when n is large. And I think a lot of you will have a good hunch for what that is, but it helps to actually substitute in some values to see exactly how this goes. So if we start off with some small values of n, so we start with 1 and we go up to 4, it looks like the 2000 log n part is the biggest part, right? Because it's got the 2000 behind it, so it seems to be a very big part of that function. But we actually don't have to go very far increasing the number of n before we have a different part of the function that ends up being the largest growing part of the function. So that is the 900n part. So you can see that as n gets larger, the 900n part is growing faster than the 2000 log n part. So everyone clear with that graph? You can kind of see how I've got in green there the 900n, and in blue we've got 2000 log n. Right. But then if we go even further out, so up to n is equal to 75, the 12n squared part is growing the fastest. And then from there on, if we go up to n is equal to 200, we can see that the 12n squared part is growing much faster than the other two parts of the function. So if we want to formalize this using the notation that we introduce specifically for this, we can say that T of n is in big O of n squared. And specifically, we have to define some upper bound to it. So I've defined 24n squared as just an arbitrary upper bound. But if we have a look at this function, if I were to do 24n squared and try and plot this on the graph, it'll always be larger than the red function here, as long as we're sufficiently far into the function. So, and we have some scary maths, but hopefully we can fully understand how this is defined, and then we can have a look at the intuitive explanation for it. So we have a function f of n is in big O of g of n, if and only if there exists n0 and c, both of these are greater than 0, such that for all n greater than n0, we have f of n is less than or equal to c of g of n. So that's just a whole bunch of mathematical nonsense. But basically, we have to define n0 and c ourselves so that we're able to define this relation between our two functions f and g. So if I want to pictographically show that, we can see that we have two functions here. We have f of n, we have g of n. And we can see that for some value n0, oops, there should be a c there that just managed to disappear. Okay, but g of n's fine. If we have some function g of n, as long as n is greater than n0, g of n is larger than f of n. So we can see that g of n makes an upper bound for f of n. So you can also read g of n grows at the same or a faster overall rate than f of n does once n is large enough. Okay, so the cusp of what we're trying to do here is give an upper bound to what our function's runtime is doing. So what's running faster? Like that? Yeah. All right. So back to the same example that we're looking at before. If we have t of n less than or equal to 24n squared, going back to this definition, or it's actually on the screen, going back to the definition, I've defined c to be 24 and I've defined n0 to be 100. And these are completely arbitrary. They just fit out for the function that I've defined. And so we've got t of n is less than or equal to 24n squared. Can I click on? It's kind of hard to manipulate this because, yeah, I know it's like Shannon. Yeah, I'm going to probably leave that, but you can have a look at that URL and have a play with the graph yourself. It's kind of hard to manipulate up here. But I could choose other functions, g of n, to make our upper bound. So we could have n cubed, we could have n factorial. We can say that t of n is of big O of n cubed, or t of n is big O of n factorial, because each of these functions give an upper bound for our runtime here. But we have a bit more definitions again. We like to choose the simplest upper bound, so we can drop all the constants. So we can see that I could have written big O of 12n squared here, but it's just easy to drop the constant at the front there. You could just do big O of n squared, right? So if we have 2n log n, we could say that that's big O of 5n squared minus 3, or we could just say it's big O of n log n. So we can say there's a constant at the front there, which is the 2, and we actually don't have to worry about the base of the logarithm. We can just write it as n log n. And I think these examples Shannon went through last week. Is that correct? Yep, I think so. So I can skip these. But then the good thing about big O is if we've now given a simplest upper bound for both of our functions, then we're able to investigate. We're able to see as n grows large, which of the functions is faster than the other functions. So we showed this just before. If I have a look at the red one is taking a longer amount of time than the blue one and the green one as n gets large. So that's kind of the intuition that we have here. We have a whole bunch of complexity classes. This can be useful for you as a reference, but you typically will see a constant time, which means no matter what the size is of your input, it always runs in the same amount of time. We have log n, which I think Shannon will go into today about. We have linear time, which linear search is such an example. We have n squared, n cubed. We can get onto exponential time and factorial time. And the thing that I wanted to show you was, so if we set n to be 10, most of these are reasonably sized. For n to be 30, which is only a little bit larger, the ones down here, we go from having 1024 to 1 billion just by increasing the size of our array by 20. And likewise for factorial, we have quite a large number, but then we have 10 to the 32, which is very, very large. And then for n to the n, it gets even larger still, 10 to the 44. So just for you to test with yourselves, and I'll let you talk to the person next to you about this if you'd like, if we have time. I think we have time. Yep. I just want you to try and give an upper bound for each of these functions, right? I'll give you a good minute or two to have a go at it. And for those of you who are there on Zoom, you can try and just send them in the chat. I think people can see that. I think people can see that on the Zoom chat there. But yeah, have a go at figuring out what the big O of all these are, and then we'll go through them as a big group. So I'll give you a minute. So for the first function, does anyone want to shout out what they think the upper bound is in big O notation? Say it pretty loud so I can hear you. N squared, but it's big O of n squared, specifically big O of n squared. And so how does that work? We can just drop the constant, right? We don't need to worry about the constant. And for f1 of n, what do we think that is? What would be the upper bound for, if we have a function 5, what's something that's going to grow larger than that? It's kind of a trick question. Is that your answer? You're just doing that? I can't see you if you do that. Okay, what I'm going to try and do, just to make it as clear as possible, I need to get decimals out, or try to. So I should actually do the previous one first. So the previous one, I believe, was 12x squared, right? The way we could upper bound this, so if we're going to put an x squared here, we just have to define some constant that we can multiply it by that will always be greater than this. So I could do like 15x squared. And appropriately set a y-axis. There we go. We can see that the blue function is always growing larger than the red function. And so therefore, I can just do big O of n squared, and we're done. Before the constant, so if I set y to be 5, I can do a constant times 1. And all I have to do is set this constant to be some value larger than 5. And of course, this function grows larger than the other. There we go. And now we can set the blue functions above the red function. I think I have to hand it back to Shannon at this point. And I hope that that gives you at least an illustration for what we're trying to do with big O notation. Try and make it an up bound here. Shannon, put the hat on.
You see, it's not so easy. The projector.
Yes.
And can we have a round of applause for Mutineer Saliba, who took control of the ship today?
Cheers, Shannon.
Thank you. I will take this back. And now we return to our regularly scheduled programming. Okay, let's clip that on. So I have provided a textbook that I find particularly helpful for exploring the concepts of big O and big O proofs. It's this one by Graham Newth and Patashnik. I find it quite readable. However, if you don't like this particular textbook but still want to understand big O, I encourage you to go out there and find one that actually suits you. There's no prescribed text on Big O. Just go to the library, pick up a few, look through and see what makes sense to you. And this is generally a good study approach that I recommend, is if you don't understand something in class that I have been going on about, try and find someone else. Maybe it'll be Liam, it'll be your own tutor who explains it in a way that you find clearer and to provide more clarity. I won't hold it against you. Now that we understand Big O pretty well, let's return to our analysis of algorithms, and in this case, linear search. So we evaluated the correctness and runtime of linear search, and we want to see if we can make it faster. So can we make linear search that we provided in class last week, where we just go through everything and then report back which element was correct at the very end? Can we make that faster? Yeah, there's a pretty obvious way. Stop when you find the right item. What does that look like in our pseudocode? So here we have our linear search pseudocode as before. While I is less than n and ai is less than x, keep going on. If I is outside the array bounds or ai is bigger than x, terminate. But this only works in a particular scenario. Can anyone see what this particular scenario is for this version of linear search? Yeah, this version of linear search actually requires A to be sorted because it relies on the fact that we terminate once AI is larger than X. Because we know then that we are in the wrong part of the array, it couldn't possibly be there anymore, and so we can stop. The only problem here is most of the time our arrays aren't sorted, and even if they are, which we can assume for the purposes of this exploration, this algorithm still has a worst case of O of n. Because what if the if the items that we're searching, if the item that we're searching for is well outside the bounds of the items contained in the array, we may not get to that stopping point until we hit the very end. So this provides us some improvement over linear search for a sorted array, but doesn't seem to be optimal. In fact, we've already seen in this class a better approach. This is the algorithm binary search that we explored with our dictionary in 2. When we have something that's sorted, the intuitive idea is to go halfway, see if you're too early or too late, throw out half the problem, and then continue on in the area where you know the value you're looking for must be found. This is a schematic version of what our algorithm that we practiced in class actually looks like. Let's say instead of a phone book, today we'll deal with an encyclopedia, and we're looking for a word on the page of the encyclopedia. Assuming we're on the right page, the right strategy is probably going to be scroll through the words. I mean, you could look halfway down, but it might take you just as long if you're a human doing this. So let's say once you're on the right page, we're just going to go through them one by one. But how do we get to the right page in the first place? We go back to our strategy that we, I forget who it was. There was someone in here who came down and demonstrated so beautifully for us how to find a name in a telephone directory. So for all the entries on the page, if you're not on the right page, to the next segment. If the topic is earlier in the book than what you're looking for, your new book that you're looking for is the left half of the book, throw everything else out, and then repeat this process, open what you've got left to the center, and go again. If, on the other hand, the thing that you're looking for is in the right half of the book, call that right half of the book your new book, and then go back up to line 3 and repeat this process again and again. Otherwise, quit. We've seen this in action, but can we prove its effectiveness? Well, one reason that we might want to look at this is because it appears that it might be faster. Because we don't have to go through all the book one by one, we've got quite an advantage. But how long actually does it take? Well, assuming there are a constant number of entries on a page, so once we're in the right spot, we only have to look through, say, 50 things, and we only have to make one step each time we halve the book, we've got a significant advantage. But how large is that advantage? Let's do the analysis. So given that we have to do C steps once we're on the correct page, we're going to have to do some number of comparisons and some setup and some work after to report back the results. That'll be our C. Then we know that we're going to run binary search again on half of the problem size. So let T of n be the time that it takes binary search to run on size n. The time that it takes to run on size n is this extra work, the finding it on the page, plus half the work that you would have done for a full-size binary search, because we're throwing out half the book. But this doesn't really give us an answer. We've gone back to one of these recursion relations that only tells us how long the problem will take to run in terms of itself. Now, thinking back a little, we've seen how to deal with recursion relationships before. We can do our proof by induction or our substitution, but in this case, our recursion relation is going to lend itself to an intuitive approach. If we think of how large our problem size is each time we throw out half the book, we get a pattern that looks something like this. In the first instance, we have a whole book, then we have a half a book, then we have a quarter of a book, then we have an eighth of a book, and so on and so forth, until we get down to one page. And the question here is, how many times can you halve a book until you get back to a single page? Well, we have a function that actually calculates this for us. If we have a book of size n, how many times can we halve it until we get back to 1? Does anyone in the audience know what this function is? What function, what mathematical function that you've seen in here and in other classes counts how many times you can you can divide something by a certain factor until you get back to 1? Anyone have an idea? Emily, I'll run the mic up to you. Exactly. So keep holding the microphone for a second. So assuming our problem is of size n, how many steps will it take for us to get back to 1? Log 2n. Perfect. And that gives us an intuition for what the big O is going to be of this function. Let's see if it bears out. So we have k terms over here, and we're dividing n by 2 each time. So we get, if we have k terms where we're just setting k to be a number that we don't know what it is yet, that's going to be the number of times we do this division. We're going to do k divisions, n on 2 to the k equals 1. That gives us this equation that we can now solve. So let's rearrange the equation. If n on 2 to the k equals 1, then rearranging C, we get n equals 2 to the k. And now we know how to solve this. As Emily said, if we take the log of both sides, we get log base 2 of 2 to the k, which is just k, and we get log n on the side. So it's going to run in log n time. Overall, if we add back in our c, we're going to do c operations log n plus 1 times. Let's multiply that out. We get O of c log n plus c. As Liam just pointed out to us, these constants don't really matter, so we can drop the c's, we can drop the constant at the end. The log n part of this that's going to grow faster, not the c. The c is just going to stay the same. That's like saying O of 1 or O of 5. We can ignore that because the log n part stays, giving us the final runtime for binary search, which is log n. If we were actually to plot this, and unfortunately we didn't get a chance to do it thanks to some projector issues, but log base 2 of n grows much more slowly than n. So for a sample value of 8, what would log 2 of 8 be? If we have a function that, if we have a problem of 8. 3, great. So 3 is smaller than 8. So if we have O of n versus log base 2 of n, and it just so happens that our problem is of size 8. For linear search, assuming it's going to be bounded by this function 8, and for binary search, it's going to be 3 steps. So obviously, quite a bit of an improvement there, just starting with a small number. Ooh, that is beautiful. I think we have a new tactic for the rest of the semester, as Liam is going to draw funny pictures of everything while I'm talking about it. So here's another challenge for you, Liam. Can you draw me a picture of binary search correctness? I don't know. This is why we're playing the game. So given that we're unable to do it with a simple picture, let's try it with an invariant. Perhaps this strategy will yield us a little more fruit. Our new invariant this time is a little more complicated than the ones we've seen before, but conceptually we're doing the same thing. Let us set a couple of variables, low and high, that are going to both be within the bounds of the array, so inclusive of O and N. As before, let's also pick some element that we're looking for X, and we'll say that X is neither in the bottom half nor in the top half. So low is bigger than high, and the value that we're looking for is not in the small half that we've thrown out or in the big half that we've thrown out. The translation of this is as above. We're still in the array because both low and high are less than or equal to n and bigger than 0, and our item is in neither of those sections. Our invariant has to start off true. So let's pick a value for low and high that would ensure for us that this is the case. If we set low to be equal to 0 and high to be equal to n, we know that if is in the array, that it's not outside, it's not less than 0 and it's not bigger than n. So that's tautologically true. We also know that low is bigger than high, and that is also bigger than or equal to n. N is less than or equal to n. So both of these kind of parts of the array are empty when we begin. The bottom half is everything bounded from 0 out to negative whatever, which there's nothing. And the upper half is everything at the end of the array out to that infinity, also nothing there. Now let's loop. So while low is less than high, while we have nothing on either of these sides, assert that P is true. Well, nothing is changed at this point, and low is less than high. We can say for sure that low is less than high, because otherwise we never would have entered this while loop. Now, choose some element M, and this is going to be the key point of binary search, that is halfway between low and high. We do this by taking the addition, the sum of low and high, and dividing it by 2. Now, those of you who are particularly astute viewers might ask, well, what happens if you get an odd number? Let's do integer division and do the truncation. And so we get a whole number every time. It might not be precisely the middle, but as long as the two halves are as close as possible to being the same size, we get our log n behavior. Now assert again that P is true, which we know it's true, and that low is less than M, which is less than high. Again, guaranteed to be true by our construction of M. Now we have two branches of binary search. So here's branch 1. If X is less than this middle point that we've picked, and we know what we're talking about here because we've done it physically. If we've opened up the book to the middle and X is less than the thing right in the middle, then in that case, set high to be equal to the middle point and throw out everything else of the array. If we're saying that X is not in the point from high onwards, that means we're going to, from this point on, discard or ignore everything in the high part of the array. So this is just a way of, instead of ripping the book up, we're just going to put a marker down, and we're going to call this marker high on this side because it's the high part of the array. It's higher than the thing we're looking for. And from now on, we're going to ignore that part. So this is instead of ripping it up. And assert our statement is true again. So low is bigger than 0. We know that because we haven't changed low. Low is less than high. We know that that's true because of the way we've constructed M. We know that high is less than n because we've made it smaller. And we also know that X is not in that top half because by definition, our array was sorted, and it's not in the top half because of our if statement here, where we say that X is less than the midpoint. So we know it's not in that top half, and we've just put high to be at that point where we know X is lower than, so we can just throw it all out. So we've asserted our statement again. Here is what it looks like if that if statement was not true. So if instead of being in the left half, X is in the right half, if it's bigger than the middle point, instead of moving high down and throwing out this half, we're going to move low up and throw out the left half. This means we're going to ignore everything on the left-hand side, everything that was too small. And now we're only going to look at the bigger things. So let's do our assert again. I'm not going to belabor the details. We know that low is still within the bounds. We know that high is bigger than low. We know that high is less than the end of the array. And we also know the key factor in this one is thanks to our if statement that X is not in the part that's being closed off by where we move low to. And because we haven't moved high, it's still trivially true that X is within the remaining part of the array. Else, if it's in neither, if X is neither higher nor lower, what must be the case? We've found X. If it's in the array and it's not in the up, and we're not too high and we're not too low, then we know where X is. So we have to stop, we found it, and we return the index that we found it. If, however, the loop exits and we haven't executed the branch where we found the value we're looking for, and it's not in the high half and in the low half, we know necessarily that it's not in the array because we've evaluated all the possible conditions, and so we return not found. We can write this out in full without the assertions. As I said before, the assertions are useful because they allow you to ensure that your code is correct, but there is a full version of binary search with all our 3 loops combined. And we know that our return M statement must be true because if it's not higher and it's not lower, it must be equal. The other key thing that I think I probably should have pointed out a second ago is the fact that this is happening in a loop. So every time when you reach the end of, this is actually critical, when you reach the end of your if statements, you do go back and reevaluate them again. Only now when you reevaluate them, you've already thrown out part of the book. And so the remainder that you're evaluating has on it the same process repeated again. So if we've already thrown out half of the top and we come back to the top of this while loop, when we do it again, we're just looking at a reduced size array. We pick the middle again, we choose which half to do, so on and so forth. And we do this k times until we're back to the single page. Unfortunately, binary search, despite being relatively simple to analyze such that we can approach it in a first-year course, is notoriously a place where people find bugs in their own code. This is true for me too, and here's a beautiful quote from John Bentley, who's written this lovely book that I highly recommend you go out and read on your own time sometime, where he talks about when programmers were asked to write binary search, 90% of them found bugs in their implementation of binary search. I also have a personal run-in with this problem. This is one of my thesis advisors, Professor Matt Blaze. And in the first year of my PhD, he said to me, well, you're a PhD student. You're obviously an advanced computer science student. You've been studying this stuff for years. Here's a whiteboard. Here's a marker. Write me binary search on the whiteboard. And it was me and 5 other PhD students. Of the 5 PhD students, how many of us correctly wrote binary search on the whiteboard? 0. So binary search, despite being a fun algorithm, is vastly improved when you use assertions, because then at least you can spot when you make bugs. And we will leave looking at the implementation of binary search to the next lecture, where we will also tackle how to get a sorted array in the first place when we don't want to use insertion sort or bubble search or bubble sort are slow algorithms. Thank you very much. And could we have another round of applause for Mutineer Liam?